about the synthesis of amino acids. You will see that there will be the same reactions that we saw before. We will see them again. So there will be lots of repetition. And you will see them again when we will talk in chapter 11 about the metabolic defect in the amino acid metabolism. Okay, so now we are reviewing the same reaction, but in the direction where we are making the amino acids, not making the amino acids. Okay? So we will talk about transamination and amidation and synthesis from other amino acids. So these are the three common ways of making amino acids. So you either make them by transamination or by amidation or by complex reactions when you make them from other amino acids. So this is what we have in your book, the categorization or the classification of the pathways for making amino acids. Okay? But before we talk about how we make them, we need to know whether do we actually make all amino acids in our body? No. Okay. Which amino acids are made in our body? Or what do we call the amino acids that we make in our body? We call them non-essential. Okay, non-essential doesn't mean that they are not important. Non-essential means they are not essential to be obtained from the diet. Okay? Because essential will mean essential to get in the diet. Why is essential to get in the diet?
Because we can make them.
Because the body will not be able to make them. Okay? So when we study the synthesis of amino acids, we will study the synthesis of non-essential amino acids. Okay? Do we have synthesis of essential amino acids? No. So when we talk about synthesis, you have to presume it is non-essential amino acids. So this is for the 20 types of amino acids that we are needing for the protein synthesis. You have to classify them according to whether they are essential or non-essential. We'll talk about arginine in a minute, but let us see the table. You have seen this table in mole 1. Okay? So this is the acronym for remembering the essential. And again, essential means that you have to get them in the diet. You cannot make them. Okay? They are essential to eat. You have to eat them every day. You have to eat the PVT, them whole amino acids, all of them, all 10 of them. Okay? طيب. So PVT, P for phenylalanine, V for valine, T for threonine, TIM, tryptophan, isoleucine, methionine, whole, histidine, arginine, leucine, lysine. So you have to remember this acronym so that you know the essential amino acids. We mentioned in the previous slide about arginine. Okay, so arginine, it says here, it is required only during period of growth or positive nitrogen balance. So it means that you can make arginine, but it will not be enough. Okay, the arginine that you make will not be enough for the body during positive nitrogen balance, and this is when arginine will become essential. Okay, so arginine is essential only during period of growth, okay, or positive nitrogen balance. So although it's classified here as essential, so you can put an asterisk here to remember that arginine is only essential during period of active growth. Otherwise, your body can make arginine, but not in enough quantities. Clear? There are also 2 amino acids which have special cases, and these are tyrosine and cysteine. We mentioned in the previous lecture how we make tyrosine briefly. Which amino acid can produce tyrosine? Phenylalanine. Okay. And phenylalanine is here. It's essential. Okay. That's why you cannot make tyrosine unless you have enough phenylalanine in the diet. Okay. Some textbooks or reference, they would like to classify tyrosine as semi-essential. What does semi-essential?
Can be both? 50-50?
Yes, you can only 50-50, no. You can only make it if you have phenylalanine in the diet. Okay? This is very important because we will study next week and we will mention today some patients have a metabolic defect, okay, where they cannot make tyrosine. Okay, they have the enzyme that needed to make tyrosine is defective. Okay, so those patients, okay, even though that you have, ideally they should make tyrosine in the body, they cannot make it in the body. So they have to be supplemented with what? Tyrosine. They have to be supplemented because they cannot make tyrosine. Okay, so just remember for now that phenylalanine is essential. Tyrosine is made from phenylalanine. That's why some books classify tyrosine as semi-essential. Similarly, cysteine is made from methionine. Remember the famous pathway where you have homocysteine production? Yes. So in that pathway, going from methionine to cysteine. So you can make cysteine from methionine. Methionine is essential. So some books classify cysteine as semi-essential. Clear?
Yes.
Okay, good. So non-essentials, where do we make them from? From intermediate of metabolism. Okay, we will see which intermediates of the metabolism will be used to make the non-essential amino acids. One more thing that you should know, that some amino acids are modified post-translationally. We have seen this in mole 1. Remember in the fibrous protein lecture in the collagen synthesis and elastin, we talked about hydroxylation. It is called post-translational modification. So after the protein is made, you can modify the amino acid. So you can modify choline into hydroxycholine. Similarly, you can modify lysine into hydroxylysine. Okay, so these are the intermediates, or some of the intermediates that we use to make the amino acids. Okay, we have seen many of these reactions before, but this is just to summarize that we can make amino acids from intermediate of glycolysis, such as 3-phosphoglycerate and pyruvate. You already know this very well by now, right? Or you can make amino acids from Krebs cycle intermediate, and you should know this by now very well. Or you can make them from other amino acids, okay? So this is the categories of the intermediates that you need to make the amino acids. Clear? Okay, so now we will talk about the different types. This first slide that we mentioned, synthesis by transamination, synthesis by amidation, synthesis from other amino acids. So let us start with the first category, synthesis by transamination. You should know these reactions now by heart. Okay, what is the first enzyme here? ALT. Okay, so to make alanine, you need pyruvate from glycolysis. You need the enzyme ALT. The reaction is reversible, so we have seen it before in the degradation of amino acid. Now we are seeing the same reaction in the synthesis of amino acids. What is the cofactor here we mentioned before? PLP, which is derived from vitamin B6. Excellent, excellent. Okay, so this is ALT. What about this one? AST. So aspartate is made from oxaloacetate. Oxaloacetate is in which pathway? Krebs cycle. Okay. What is the enzyme we said? AST. What is the cofactor? Again, it is the same cofactor. Okay, so this is how we make aspartate. What about glutamate? What is this enzyme here? We can make glutamate from two reactions. This is one of them. Okay? So this is aminotransferase. Which aminotransferase is it?
ALT or AST? Yeah, ALT or AST.
Okay, it could be any aminotransferase. Remember we said that aminotransferases are classes of enzyme. Okay? And we said that all amino acids in transamination reaction will donate the amino group to a common acceptor, which is alpha-ketoglutarate. Okay, so this is the keto acid here. So alpha-ketoglutarate is a common acceptor of all amino group in transamination reaction. And once you add the amino group to alpha-ketoglutarate, you will generate glutamate, which is an amino acid. Is this the only way to make glutamate? No. Yes. We have seen the reaction glutamate dehydrogenase. And we call the reaction going this way, we called it what? Oxidative deamination. What does oxidative deamination mean? Which type of reaction we have?
Oxidation.
Oxidation and deamination. Okay? So here, who is oxidized, who is reduced?
NAD or NADP.
Who is oxidized? Glutamate is oxidized into alpha-ketoglutarate. It is oxidized and deaminated. Okay? And who is reduced? NAD or NADP. We said that this enzyme is unique and no, it can use either of these two cofactors. Okay? So this is oxidative deamination going from glutamate to alpha-ketoglutarate. But we're talking here about the synthesis, so we have to look at it in the other way. Okay. So what will be the reverse of oxidative deamination?
Reduction.
Okay, so the reverse of oxidative will be reductive. And the reverse of deamination will be amination. So alpha-ketoglutarate will be reduced and it will be aminated. Okay? Where is the amino group coming from? It's free ammonia. And where is the electron source? From the cofactors, either an ADPH or an ADH. So these will be oxidized and this one will be reduced. So what determines whether the reaction will go in this way or in this way? Depending on the need of the cell. So after a protein-rich meal, glutamate level will be high, and as a result, the reaction will go in this direction. If there is too much ammonia accumulating inside the cell, when the level of ammonia is up, okay, elevated, then the reaction will go in this direction because ammonia is toxic. So the cell will try to gather this ammonia inside glutamate and then in glutamine. Okay? So this is why we can go in either way, depending on the need of the cell. Too much glutamate, we have oxidative deamination. Too much ammonia, we have reductive amination, and then we can form glutamate. Okay, so this is the case of alpha-glutamate. You know, it's a unique amino acid in that it can be formed by transamination and also by reductive amination. Okay, now we finished category A, which is synthesis by transamination. What is category B? Synthesis by amidation. Okay, if we look at glutamate and glutamine, what is the difference between glutamate and glutamine?
Glutamine has more amino groups.
How many amino groups we have in glutamate?
One.
In glutamate, we have one. In glutamine, two. Where is the second amino group in glutamine? Remember we talked about alpha carbon, the H, carboxyl group, the amino group, and the R. So here we have an R that has an amino group attached to the CO. Okay? So we call amide. Amides are actually carboxylic acid derivatives. The OH group here is replaced by amino group. So they are amide. That's why we call the reaction amidation. And the enzyme is glutamine synthetase. Is this reversible? No. What enzyme will be needed to go from glutamine to glutamate? Glutaminase. Good. Okay, so this is amidation. So we're adding the second amino group as an amide linkage, and free ammonia is the source for this amino group. Do you know another amino acid which is formed by amidation? Asparagine. Asparagine is formed by amidation of aspartate. Again, the same scenario. Aspartate has one amino group. Asparagine has two amino groups. Second one is an amide linkage in the R. Exactly the same thing. We need asparagine synthetase to make asparagine. To break asparagine, you need asparaginase. Anyway. Okay, now let us review. Very good. Yes.
شلون بكون مع عبد الله؟ كان عندي هيك صور
Who's going to answer this question?
Yeah.
Can you answer the question? I love Australian accent. I want to listen to your Australian accent. I don't have one. You don't have one? How come? Okay, who wants to answer this question?
Yeah.
Yes, no. What's your name? Abdurrahman? Okay, please, Abdurrahman, raise your voice, please.
Okay, alanine is for A, pyruvate.
Okay, so alanine is made from pyruvate, yes?
Glutamate is made by alpha-ketoglutarate.
Yes?
And aspartate is made by oxaloacetate.
Great, thank you. Well done, Abdurrahman. Okay.
Good boy.
I will ask you. And then no one will say good boy. How to make proline? Only Bashir would need to answer this question in the exam. How to make proline. The rest of you are not required to make proline. Just you should know that we can make proline from glutamate. Okay? Well, it's a special exam paper for you. Okay. Now, conversion of serine and glycine. We mentioned this before. Now we're looking at it again. Look at the structure. Who can tell me what is the difference in the structure between serine and glycine and how we form each of these amino acids?
We have methyl group.
Which one has a methyl group?
Serine.
Serine has a hydroxymethyl group. Okay. So if we want to go from glycine to serine, what do we need to add to glycine? So we need to add the methyl group. So from glycine to serine. We have to add the methyl group. And who's going to be the methyl group donor? Okay, pay attention to the name. It's methylene tetrahydrofolate. Okay, the methyl group is attached here to the 2 nitrogen. So it's called methylene tetrahydrofolate or 5-10 or N5 and 10 because there is a nitrogen on carbon 5 and 10. So it's called N5 and 10 methylene tetrahydrofolate. This is tetrahydrofolate. Okay? Right. So, what is the enzyme that is needed here?
Transferase.
Yeah, it's transferase. What are we transferring? It's hydroxymethyl, so it's written here. Hydroxymethyl, because we are transferring a methyl and a OH, and we are adding it to form serine, because we can't, we have to choose one, whether glycine or serine, so they chose the bigger structure. So it's called serine hydroxymethyl transferase. Okay, this is the donor of the methyl group. And if someone has a folic acid deficiency, this would interfere with the making of serine or glycine. THF is the abbreviation for tetrahydrofolate. Okay, so this is just synthesis of serine from glycine and synthesis of glycine from ferine. So in one way you would have to donate the methyl group. So it's the tetrahydrofolate will accept the methyl group and will become methylene tetrahydrofolate. Okay, so it is reversible reaction, again depending on the need of the cell. Now we come back to this reaction that we started talking about last week. Okay, so synthesis of cysteine from methionine. Okay, how we make cysteine from methionine? In making cysteine from methionine, we will produce this dangerous molecule called homocysteine. Why we said homocysteine is bad? Why homocysteine is bad? Okay, it will cause endothelial cell damage, injury to endothelial cell, and can lead to the occlusion of the blood vessels. Okay, and you will learn in your CVP blocks that occlusion of the blood vessel can lead to something like heart attack or stroke. Okay, so we can, as I mentioned before, to make cysteine, you have to have enough methionine in the diet. Okay. Who can review the steps in making cysteine, because you are required to know all of them?
بشير صحيح والله ماشي.
Who can review the reaction? It's written in front of you, but in the back they cannot see it very well. Who can review what is the steps here? So in making cysteine, first you need to add the adenosine to methionine, and it will become SAM. Okay, what is SAM? It's methionine plus adenosine. Where is the adenosine coming from?
ATP.
ATP. So adenosine is ATP without the P, without any P. And this SAM molecule is unusual in the fact that it is high energy molecule but without phosphate group. Okay? So now we have this SAM, adenosyl methionine. So the S means that the adenosine is attached to the sulfur. Okay? That's where the name SAM comes from. It has a very active methyl group that you need to get rid of. So who will take this methyl group? A molecule which is a methyl acceptor such as norepinephrine. So once you donate that methyl group, the molecule will become SAH, which will be hydrolyzed. Okay, you will remove the adenosine group, you will get the homocysteine, the bad molecule. Then we have two more reactions where homocysteine will combine to serine, another amino acid, to form cystathionin. And the enzyme is cystathionin syntase. We will come back to it next week because there is a metabolic defect. Some people have metabolic defect in this enzyme. Then cystathionin will be broken down by cystathionase to form cysteine and alpha-ketobutyrate. The important thing is that you remember this enzyme here, and that B6 is required to make cysteine. And this nasty molecule here is involved in the pathway leading to the formation of cysteine. Okay, what can be the effect of having high levels of homocysteine? They found that the higher the level of homocysteine, the higher the rate of death from cardiovascular disease. Okay, so patients who have very elevated homocysteine in their blood, they have much greater risk compared to those who have low homocysteine level in the blood. Okay, and this is because, as we said, it can lead to oxidative damage, inflammation, endothelial dysfunction, and they are independent risk for occlusive vascular disease. What do we mean by occlusive vascular disease? Yeah, so there will be narrowing or blockage of the blood vessel. There will be an occlusion. Who had a question here? Someone was, yes?
What's the use of cysteine in our body?
Cysteine is an amino acid which is present in, you need it to make proteins. Our proteins are made from 20 amino acids. Cysteine is one of them.
You don't have this reaction in our body.
جاسوس
Just to avoid the reaction.
عشان هذه كان هذه كان
It's a protein. You know, it's one of the 20 building blocks of the protein.
Especially with the enzyme deficiency to produce we will make them stop for the full production consent.
Yes. Okay.
ايوه
في deficiency process.
Any deficiency, you will have to either supply the diet which is rich in this particular amino acid, or just have supplement of this amino acid. Okay? So, and they found that plasma levels of homocysteine are inversely related with folic acid B12 and B6. Why do you think level of homocysteine?
Required making
Okay, B6 is needed here. So if you don't have enough B6, you cannot make cysteine out of homocysteine. And B12 and folic acid, you can convert any excess homocysteine into methionine. Actually, if a patient is being diagnosed with elevated level of homocysteine, he will be prescribed supplements of B6, B12, and folic acid. Okay? So supplementation with these 3 vitamins will reduce circulating level of homocysteine. Okay, homocysteine is very important. One student from this college has written an article, a review article about homocysteine. That's why I put the link here for this article. It was written together with Professor Paul. Just to give you an idea, you can open the link, have an idea about how bad homocysteine, and people can write review article just about one molecule. Okay. Also, homocysteine level were found to be, as we said, inversely related with folic acid. We just mentioned this. But what is the importance of folic acid? Women who are deficient in folic acid, they have the risk of having a baby which has a spina bifida. What is spina bifida? Yeah, it's a type of neural tube defect, and spina bifida is the worst of them, where there is an opening in the neural tube. That's why, to avoid this, women who are planning to become pregnant, they need to have supplementation with folic acid. Why early in the pregnancy? Because this is when the neural tube will start forming. So it's advised not only for pregnant women, also for women who are planning to get pregnant. And they need to take it for the first 3 months of pregnancy. Okay, the last slide today, we'll talk about synthesis of tyrosine. And it's made from the amino acid phenylalanine. What is the difference between phenylalanine and tyrosine? OH. Okay? So the enzyme hydroxylase is needed to hydroxylate phenylalanine to make it tyrosine. This enzyme, we will learn next week, is deficient in people with phenylketonuria. What is phenylketonuria? PKU. Okay? Why phenylketonuria, not phenylalaninuria? Because phenylalanine, once it cannot be changed to tyrosine, it will accumulate and it will change into phenylketone. And phenylketones are harmful, so they can cause mental retardation because they will affect the nervous system. That's why, and we will talk about this in detail next week, newborns have to be screened at birth for many metabolic defects, and phenylketonuria is one of them. Because if you detect the defect early, you can, by dietary changes, you can give them a special type of formula milk in order to avoid giving them phenylalanine, and therefore they will not have phenylketones, and therefore they will not have the mental retardation. The cofactor here is tetrahydrobiopterin, or THB, not tetrahydrofolate. So in an exam you will have multiple choices, and you will have THF and TH3. Make sure you know that for phenylalanine hydroxylase, we need tetrahydrobiopterin, not tetrahydrofolate. Okay? We will come back to this reaction. That's why, please, before you come to class next time, make sure you have gone through your slides of 9 and 10, because 11 will talk about all the diseases that affect the reactions that we have seen before.